we'll move on now. So our second speaker is Kiran. If you could share your screen, please.
Yep.
So Kiran Sreedhar Ram from Charles Darwin University.
Yes.
If you don't mind getting your screen shared, please.
Just a moment, please.
So Kiran will talk about characterizing exciton generation in bulk heterojunction organic solar cells. Interesting, we're kind of almost related topics here. So please go ahead and give your talk when you're ready.
Thank you so much and good afternoon. I thank you for giving me this opportunity to present this. And the topic for today's presentation, as he has mentioned, is characterizing exciton generation in, you can hear me, right? Can everybody hear me?
Yes, that's very good. Hear you clearly. Yes, thank you.
Yeah, the topic for today is characterizing exciton generation in bulk heterojunction organic solar cells. This is based on a paper that has been published recently in Nanomaterials by our team. The co-authors of this paper are Human Medilrath, David Ompong, Daniel Dotsiavo Setsofia, and Jay Singh. So I'll start off. I'm doing PhD at Charles Darwin University, so I'll start off with my motivation. I'm doing PhD in organic solar cells, studying them and to improve its bulk conversion efficiency and stability. So this is the motivation for my research. Organic solar cells have low manufacturing cost compared to inorganic solar cells because there aren't any high temperature processing techniques in it, so they have low manufacturing cost. And these organic solar cells can be made into flexible thin films, so they can be easily corded onto buildings or automobiles. As mentioned, because they can be made into very thin films, unlike inorganic solar cells, the amount of raw materials required is very less. So less raw materials means less cost. And we can provide solar panels at reduced cost, organic solar panels in the future to the customers, and that will make the customers very happy. So these are the motivations for my research. And introduction to today's topic. We have simulated and analyzed the following in 3 bulk heterojunction organic solar cells. First is we have simulated and analyzed the interference of incident and reflected electric field of the electromagnetic radiation in the active layer as a function of the thickness of the active layer. Second, we have simulated the exciton generation rate in the active layer as a function of the thickness of the active layer, and also the exciton generation in the active layer as a function of the thickness of other layers. Those are electrodes and transport layers. I'll take you through a briefing about the fullerene and non-fullerene acceptor-based BHJ organic solar cells. BHJ OSC's abbreviation is bulk heterojunction organic solar cells. The fullerene acceptor-based BHJ OSCs have been around for a while, and there are numerous researchers already on the topic. And even our team has done some researches on it. One of them is Human and his team has studied the exciton generation rate as a function of the thickness of active layer for fullerene acceptor PCBM based BHJ OSC, both in its conventional and inverted configurations. But these fullerene acceptor based BHJ OSCs have some disadvantages. They have limited chemical and energetic tunability, narrow range of absorption spectrum, and unstable morphology. So scientists have been working on finding some alternative materials, and recently they have come up with the non-fullerene acceptor-based bulk heterojunction organic solar cells, and therefore the research focus moved from fullerene acceptor-based BHJ OSCs to non-fullerene acceptor-based BHJ OSCs. Because of these following advantages of these non-fullerene ones over fullerene ones, they are easier to process using solution chemistry. We can have high VOC while maintaining JSC, and the band gap of these non-fullerene acceptor materials can be easily tuned. And the NF BHJ OSCs, the CT excitons generated in them will have low binding energy compared to that of fullerene acceptor-based bulk heterojunction organic solar cells. So keeping that in mind, we found that there is a research gap that exists in this field now. For non-full acceptor-based BSD OSCs, research gaps exist in studying and simulating the interference of incident and reflected electric field of electromagnetic radiation in active layer as a function of the thickness of active layer. Exciton generation, right, in the active layer as a function of thickness of active layer, as well as the thickness of other layers like electrodes and transport layers. So our team worked on this and published that paper. So these are the three structures. These are the three structures that we have used to simulate the interference effect and exciton generation rates. First structure is OIC1, which is an inverted non-fullerene bulk heterojunction organic solar cell. Second is OIC2, which is a conventional non-fullerene bulk heterojunction organic solar cell. And third is OIC3, which is a conventional fullerene bulk heterojunction organic solar cell. I'll give you a briefing about the difference between inverter and conventional. In inverted structure, after substrate, this ITO indent in oxide is cathode, and then followed by ZNO, which is an electron transport layer, and then the active layer, followed by MOO3, molybdenum oxide, which is a Hall transport layer, and aluminum acts as an anode. Now coming to the conventional, that is inverted, that's the opposite. After the substrate glass, it is ITO, which acts as the anode, then P dot PSS is Hall transport layer, then you have got the active layer, then PFM-BR is the electron transport layer, and aluminum is the cathode. So using these three structures, we have simulated the interference effect and exciton generation rates and studied them. Okay, and this is the, we have used optical transfer matrix method to simulate and study them. And this is the figure for performing the optical transfer matrix method. We have considered this cell to be a multi-layer stack with substrate being one layer and layer J as the active layer. You can see here that this is the incident light and EJ plus is the electric field of the electromagnetic radiation that is going in the positive direction. And this EJ minus is the electric field of the electromagnetic radiation that is going in the opposite direction. That is from reflected light from interfaces and also from aluminum layer or the rear electrode. And these are the equations that we have mainly used for the simulation method. And again, Gj dot is the total exciton generation rate. Gj dot of X is the position dependent exciton generation rate. Gj dot of X comma lambda is the position and wavelength dependent exciton generation rate. And Eg of X comma lambda is the position and wavelength dependent electric field in the active layer. Now moving on to the next. This is a complex of fatty indices of the active layer blends that we have used. As I mentioned, we have used two blends, two active layer blends. One is P3H3PCBN and other is PBDBTSF-IT4F. P3H3PCM is the fullerene one and PBDBTSF-IT4F is a non-fullerene one. And this one is the refractive index NJ for both of them. And this is the extinction coefficient KJ for both of them. So using this, we have simulated the results. And before going to the main simulation, we have validated simulation. This we have done by simulating the JSC, short circuit current density for OSC1, which is the blue curve, OSC2, which is the dash black curve, and OSC3 is the dash dotted blue curve. And then we compared them with the experimental values already available in literature. These red circles represent the experimental JSC of OSC1, and the red star is that of OSC2, and the crosses, red crosses are that of OSC3. And from this, we found that they are in good agreement. So that gives us a validation that our simulation technique is in the right way, correct. So using that technique, then we simulated the electric field and also the exciton generation rate. This is the contour plot of the normalized modulus of electric field in the active layer of OSC1, and this is exciton generation rate in the active layer of OSC1. You can see here that the there are three figures. See, one, this is 35 nanometer active layer thickness, these two figures. That's why the position is from 0 to 35. And this is 90 nanometer active layer blend, OIC1. So it's from 0 to 95, not 90, 95. And then we have this 180 nanometer thick active layer. So it is from 0 to 180. So you can see here that there are bright spots and dark spots. Here in the top row, the bright spots represent regions of maximum constructive interference of the electric field, and the dark spots represent regions of minimum constructive interference. Similarly, here in the electric field graph, the bright spots represent, sorry, this is the exciton generation graph. Here, the bright spots represents regions of maximum exciton generation rate, and that is maximum photon absorption. And the dark regions represents that of minimum photon absorption or exciton generation. If you compare these three graphs, you can find that the middle one has better electric field, constructive interference of electric field compared to first and the third, A and E. So, and if you consider these three graphs, the bottom graph, the exciton generation rate is much higher in the 95 one, compared to 35 and 180. So this one should give optimal photovoltaic performance, 95 nanometer active layer thickness. And we have also found on literature that this OIC1 structure has optimal active layer thickness of 95 nanometer. And we have also found that better the overlap of regions of constructive interference, maximum constructive interference over the maximum photon absorption region, then better the photovoltaic performance. You can see it here, how it affects. This has got better overlap compared to these ones and these ones. Now, moving on to the influence of other layers on OIC1. We have simulated the influence of the variation of thickness of other layers like electrodes and transport layers on the generation rate in the active layer of OIC1. And you can see that this black curve represents the optimal thickness, active layer thickness, Lj equal 95 nanometer. And the red curve represents Lj is equal to 180 nanometer. You can see here that this is layer one. This is for layer one. Layer one is indium tin oxide. Indium tin oxide here is the cathode, because this is an inverted non-fluorine structure. So you can see here that the maximum generation rate is around the thickness L1 when it is around 150 nanometer. So we have checked it in the literature. The experimental value also is optimal thickness is also 150 nanometer. So it matches with the simulated result. Now here, the thickness L2, variation of GJ with thickness L2. L2 is zinc oxide here. Zinc oxide is the electron transport layer. And you can see the black curve. If you observe the black curve, it first decreases, then increases, and again decreases. And the maximum generation rate is when L2 is minimum, or when L2 tends to 0, thickness tends to 0. But we know that this is no. Zinc oxide layer helps in, because it's an electron transport layer, it helps in reducing the recombination loss as well as reduce the contact resistance. So the thickness of L2 cannot be 0. So we have taken thickness around 30 nanometer, and it is also matches with the experimental available value in literature, which is 30 nanometer thick no. Now moving to the next layer, L4. Layer 4 is MO3, that is whole transport layer for OIC1. You can see that for the optimal thickness, Lj equal 95 nanometer curve, the maximum thickness, maximum generation rate is around when L4 is 10 nanometer, 10 nanometer. And that also matches with the experimentally available data from literature. And then we move on to the layer 5. Layer 5, unlike other layers, has a constant and doesn't have oscillation. These have oscillations because of interference effect. But in case of aluminum, the exciton generation rate increases, and at around 50 nanometer thick aluminum, it becomes constant. This is because after 50 nanometer thick aluminum, almost all of the light is reflected back into the active layer, and therefore the exciton generation rate remains constant. And any value above 50 nanometer is acceptable, and more And we have taken 100 nanometer, which is the most accepted fabrication thickness for aluminum for organic solar cells. And then we move to the influence of other layers on organic solar cell to OSC2. And we found that the layer 1, layer 4, and layer 5, the trend is exactly same as that of OSC1 for OSC2. So we have not shown it here, but we have found that the trend is slightly different for layer 2. As you can see here, the black curve represents the optimal thickness, and you have to note here that the optimal thickness for OSC2 is 100 nanometer, and here the thickness, as the thickness increases, generation rate decreases and then becomes constant for a small thickness and then decrease again. But for OSC1, it was like it increases, then it decreases, then increases and again decreases. But that is not the case for OSC2. And here also you can see the generation rate is maximum when the thickness of here the layer is P dot PSS is minimum or 0, but this is Hall transport layer. As I mentioned before, in order to reduce recombination loss and contact resistance, this cannot be made 0. Therefore, we have taken it to be around 30 nanometer again, which it agrees with the experimentally available data in literature. Now we have compared the position-dependent exciton generation rate in OSC1 and OSC2. You can see here the black curve represents the position-dependent exciton generation rate in OSC1, and the dashed red curve represents the position-dependent exciton generation in OSC2. You can see that for the entire thickness, this OSC1 has a better exciton generation rate compared to OSC2. So we can say that OSC1 has better photovoltaic performance than OSC2. One more thing that you can notice here is that the optimal thickness of OSC1 is 95 nanometer, which is an inverted structure, and that of OSC2 is 100 nanometer conventional structure. Even though this difference is only 5 nanometer, when you do it in bulk manufacturing, even this 5 nanometer can help to reduce the cost. So I believe that OSC1 can be made cheaper compared to OSC2 during bulk fabrication. Now we are going to the influence of other layers on OSC3. OSC3, we have to remember that it is a Fullerene acceptor based conventional organic solar cell. So the active layer is P3S3 PCBM. And we have also found that for layer 4 and layer 5 of OSC3, the trend is exactly similar to that of OSC1 and OSC2. So we have not shown it here, but for the the layer 1 and 2, it is a bit different. Here you can see this black curve represents the optimal active layer thickness, and it is around 80 nanometer for P3S3 PCBM based Bulk-heterojunction organic solar cell. And the oscillations are bigger, and from that we can infer that a slight change in the thickness of the layer 1, which is ITO, indenting oxide, can lead to a large difference in photovoltaic performance compared to that in OSC1 and OSC2. When you look at the layer 2, you can see this the curve is slightly different from that of OSC1 and OSC2, but you can see here that the generation rate here also is maximum when the thickness of L2, which is P dot PS, is minimum. That means but in the case of P dot PS is a Hall transport layer, so it cannot be made 0. So we have taken the thickness around 45 nanometer due to reasons we have already mentioned, and that is also in agreement with the data already available in the literature, experimental data. Now these are the optimized layer thicknesses of all three OSCs, layer 1, layer 2, layer LJ is the active layer. We have put LJ here because of the equations we are given LJ, then L4 and L5 for OSC1, OSC2, and OSC3. And in conclusion, characterization of exciton generation rate has been carried out in 3 BSJ OSCs, OSC1, which is an inverted non-Fullerene structure. OSC2 is a conventional non-Fullerene structure, and OSC3 is a conventional fuller and acceptor-based structure. It is found that the regions of the overlap of the constructive interference of forward traveling and reflected light waves and those of high photon absorption regions depend on the thickness of active layer, which is used to optimize the thickness of active layer with the maximum overlap. The rate of total exciton generation rate, GJ, in the active layer have been optimized with respect to the thickness of each layer in the device structure. And these are the references. Thank you.
Thank you, Kiran, for your presentation. So quick round of applause. I'll open it up for questions from the audience. If you can just unmute yourself and ask questions if anyone has any for discussion. If not, I guess I'll ask a question. I suppose there's a lot more to the story than just the electric field strength inside. So can you kind of comment on the broader picture, I guess, as far as the optimization work that you're trying to achieve, and you know, any future directions that you would recommend there in terms of other things to consider?
In our paper, we are actually trying more than optimization. We are trying to understand these three structures has already been fabricated experimentally. So we were trying to understand the reason behind why they chose those optimized thicknesses. So we're trying to explain that based on the electric field and the exciton generation rates.
Okay. Okay. Were there any other questions from the audience? Okay. If not, then I think everyone please join me in thanking both of our speakers for today.